It's useful to pretend like all materials in the universe can be broken down into a category of insulator, electrical insulator, or electrical conductor. Now that's not completely true. There are semiconductors and superconductors and other exotic forms of electrical materials, but for most introductory physics classes and problems and tests, you can get pretty far assuming that it's either an insulating material electrically or a conducting material electrically. And before I talk about the differences between these, here I have two solid cylinders of either an insulating material or a conducting material. Before I talk about the differences, one similarity is that both insulators and conductors are composed of a huge number of atoms and molecules. And these atoms and molecules, whether it be insulator or conductor, are composed of a positively charged nucleus and a negatively charged swarm of electrons that surround that nucleus. Another similarity is that for both conductors and insulators, the positively charged nucleus cannot move. I mean, it can wiggle around and jiggle just from thermal vibrations, maybe a little bit in place, but it can't travel freely throughout the material. For either an insulator or a conductor, as long as it's a solid, if it was a fluid, I suppose these things could move and migrate around, but for a solid, the positively charged nucleus is fixed. They're stuck. The thing that might be able to move are the negatively charged electrons, and here's the difference. There are electrons in a conductor that can move about relatively freely. These can move around with almost no resistance. Whereas for insulators, the key difference is that these electrons cannot move around freely. These don't have the right energy levels and bands in order to make these electrons move around freely. They're also stuck. For insulators, everything's basically stuck. These electrons might be able to jump around in their own atom or get shared with a neighboring atom, but it can't jump around freely from atom to atom and travel throughout the insulator. For the conductors, the electrons can do this. That's the key difference. Now, the electrons aren't going to just do this on their own. They'd have to be compelled to start moving by hooking this up to a battery or setting up some sort of electric field or force. And if that did happen, then the electrons in a conductor could start migrating down the line. But in an insulator, the electrons are stuck, which might make you think that, well, okay, shoot, for electrical materials, all we really care about are the conductors. The insulators we just use if we don't want electrical interaction. And while that's somewhat true, it's not completely true, because if I set this insulator up to a battery, or I set up some sort of electric field or force in here, even though the electron in an insulator can't jump from atom to atom, what it can do is it can shift. This nucleus and the cloud of electrons can kind of shift a little bit. Positive maybe this way, and then the negatives over on the other end. So what you'd get is that overall, this side of the atom would be more negative, and this side of the atom would be more positive. And even though the electron doesn't move and the electrons don't move, now because this is set up where the positive is shifted from the negative, this material, if you get all of them to do this, or a lot of them, this can create an overall electrical effect where this insulator can interact with other charges nearby and exert forces on them. So even though the charges can't flow through an insulator, they can still interact electrically. Now, let's see what happens if we add extra charge to these insulators or conductors. I mean, the way they started off right here, we had just as many positives in the nucleus as there are negatives surrounding them, and that's true for the conductors and insulators. What happens if we add extra charge? Maybe we add extra negatives into here. Then what happens? Well, it'd get really messy if we tried to draw it with all the atoms. So since these all cancel out their overall charge, I'm not going to draw every atom and nucleus. I'm going to just pretend like those are there and they're all canceling out. I'm just going to draw the actual extra charge. So let's say we added extra negative charges to this insulator. What would happen? Let's say I just add a negative charge here and a negative charge there and here and there, and I've added a bunch of negative charges to this insulator. What would happen? Well, we know these negatives can't move throughout an insulator. Charges can't flow through an insulator, so they're stuck, which means for an insulator, I could charge the whole thing uniformly if I wanted to, where the charges spread out throughout the whole thing. Or I could make them bunch up on one side if I wanted to, and they'd be stuck there. But the point is that they're stuck. For a conductor, what would happen? If I tried to put a negative here and a negative there, some extra negative charge on a conductor, they don't have to stay here if they don't want to. And if you put extra negatives in here, They're not going to want to because negatives repel each other. Just like opposites attract, like charges repel. So what are they going to do? Well, this negative is going to try to get as far away from the other negative as it can. It's going to go over here. This negative is going to try to get as far away as it can. It repels it. Now, it can't jump off the conductor. That takes a lot more energy. But they can go to the very edge. And that's what charges do for conductors. If you got a solid conducting material, you put extra charge on it, it's all that charge is going to reside on the outside edge. Whether you've added extra negative or positive, always on the outside edge. So you can only add charge to the outside edge for a conductor, because if it wasn't on the outside edge, it'll quickly find its way to the outside edge because all these negatives repel each other. And I said this is true for positives or negative. You might wonder, how do we add a positive? Well, the way you add a positive is by taking away a negative. So if you started off with a material that had just as many positives as negatives and you took away a negative, it's essentially like adding a positive charge in here. But again, the net positive charge, the net negative charge always resides on the outside edge of a conductor because charges try to get as far away from each other as possible. So what physical materials actually do this? What physical materials are insulators? These are things like glass is an insulator, wood is an insulator, most plastics are insulators. All of these display this kind of behavior where you can distribute charge and the charge can't flow through it. You can stick charge on it. In fact, you can stick charge on the outside edge and it would just stay there. And there's conductors. These are things like metals like gold or copper is typically used because it's kind of cheap, cheaper than gold certainly, and or any other metal. Silver works very well. These are materials where charges can flow freely through them. So now that we see how conductors and insulators work, let's look at an example. Let's say you had two conducting rods. Say these are made out of metal, and one of them has a net amount of negative charge on it, which is going to reside on the outside edge, because that's what net charge does on a conductor. But this other rod, this other metal conducting rod, does not have any net charge on it. What would happen if I took this first rod, touched it to the second rod? You could probably guess. Charges want to get as far away from each other as possible. So these negatives realize, hey, if we spread out, if some of us go onto this rod and some of us stay here, we can spread out even farther away from each other. That's what they would do. If these rods were the same size, you'd have equal amounts on each. If this second rod was bigger, more of them would go onto the second one because that would allow them to spread out even more, and some would stay on the smaller one. So that's charged by just touching something. That's easy. You can charge something also. You can get clever. You can do something called charge. You can charge something by induction, it's called. And what does this mean? Charge by induction says, all right, first imagine I just take this and I bring it nearby, but don't touch it. I just bring it nearby this other piece of metal and I don't touch it. What would happen? Well, there's negatives in here. I haven't drawn them. And there's positives in here. The negatives can move if they wanted to. Do they want to? Yeah, they want to. These negatives are coming nearby. They want to get as far away from them as possible. So even though there are already some negatives here, a net amount of negatives are going to get moved over to this side. So they were located with their atom on this side, but they're going to want to get away from this big negative charge, so they move over to here, which leaves a total amount of positive charge over here, i.e. there's a deficit of electrons over here, so this side ends up positively charged. And you might think, okay, well that's weird, they spread out. Does that anything else happen? Yeah, because now these positives are closer to the negatives than the negatives are, and these positives in this charged rod are attracting these positives. These negatives in this conducting rod are attracting these positive charges because like charges repel and opposites attract, but they're also repelling. These negatives in this rod are repelling these negatives. Do those forces cancel? They actually don't, because the closer you are to the charge, the bigger the force. This would cause this rod to get attracted to the other rod. So that's kind of cool. This means if you took a charged rod, brought it to an empty soda can, let that can sit on the table in this orientation so it could roll. If you bring the rod close, the can will start moving toward the rod. It's kind of cool. You should try it if you can. But that's not charged by induction. Charged by induction is something more. It says, all right, take this piece of metal and conduct it to ground. What's ground? Well, it could be the ground. If you took a big metal pipe, stuck it in the ground, that would count. Or any other huge supply of electrons, a place where you can gain, steal, basically take infinitely many electrons or deposit infinitely many electrons, and this ground would not care. So the frame of your car, the actual metal, is a good ground because it can supply a ton of electrons or take them. Or a metal pipe in the earth, some place you could deposit electrons and take them, and that thing won't really notice or care. Now what would happen if I bring this negative rod close to this rod that was originally had no net charge? Now, instead of just going to the other side of this, they say, hey, I could just leave. I'm going to get the heck out of here. These negatives can leave. A whole bunch of negatives will start leaving. And what happens when that happens is that your rod is no longer uncharged. It has a net amount of charge now. They won't all leave. You're not going to get left with no electrons in here. There's going to be some electrons in there. But some of the electrons will leave, which means this rod, which used to be uncharged, now has a net amount of positive charge in it. So I've charged this rod without even touching it because I let those negative electrons leave. And if I'm clever, what I can do is I can just cut this wire before I take away the thing that induced the charge. If I remove this now, move it far away, what these negatives would have done is they would have said, phew, okay, I'm glad that's over. Now I can rejoin. I'm attracted to this positive again. I'm going to rejoin my positive, and this thing would become uncharged again, but now they can't get back. They're stuck. There's no way for these to get back because you've cut the cord here and you've permanently charged this piece of metal without even touching it. It's called charge by induction. It's a quick way to charge something up. But let me show you one more example. Everyone's tried this. You take a balloon. What happens? How do you charge it up? You rub it against your hair. It steals electrons from your hair and the balloon becomes negatively charged. What do you do with it? You know what you do with it. You take this thing, you put it near a wall or a ceiling, and if you're lucky, it sticks there, which is cool. How does it work? Well, remember, this is an insulating material, rubber. The ceiling's an insulating material. Electrons aren't getting transferred, but even in an insulating material, the atom can reorient or polarize by shifting. The negatives in that atom can shift to one side. The other side becomes a little more positive. And what that does is it causes a net force between the ceiling and the balloon because these positives are a little closer. So these positives are attracting the negatives and the negatives are attracting the positives with a little bit greater of a force than these negatives are repelling the other negatives in the ceiling. And because of that, because the ceiling is also attracting the balloon and the balloon is attracting the ceiling with greater force than the negatives are repelling the balloon can stick because of the insulating material's ability to polarize and cause an electric attraction. This is what I said earlier. Even if it's an insulator, sometimes it can interact with something electric because the atom can shift and polarize.